So hello and welcome back to the Coding for Medicine series, where we learn how to code by making useful medical applications. My name is Chris Lovejoy, I'm a data scientist and a doctor based in London, and today we're going to train a neural network to predict who's not going to attend their hospital appointments. And in the process of doing so, we're going to learn how to download data from Kaggle, how to then clean that data and prepare it for training, how to train a neural network, and then how to analyze the results of that. So this video is going to be focused on how to actually code it. We're not going to go too much into the theory behind how neural networks work and that sort of thing. If you are interested, I have made other videos on that, so have a look in the link in the description below. So with that being said, let's get into today's problem. So why are we trying to predict who's not going to attend their medical appointments? Well, the reason for that is because it costs a lot of money, in the region of a few £100s, every time somebody is booked for a medical appointment and then doesn't attend. Now, if we give a phone call before asking somebody if they're going to come to their appointment, then that increases the chance that someone will come, and it also means that if they're not going to come, we can then cancel that appointment and give it to someone else. However, we don't really want to have to go around phoning every single person who's coming for a medical appointment. So therefore, if we can predict who's at highest risk of not attending, give them a quick phone call, that can actually save a lot of money, save a lot of doctors' time, a lot of nurses' time by just increasing the number of people who are attending their medical appointments. That being said, this is something that a research group in London looked into. They trained a model and that was published in Nature Digital Medicine, a link in the description for those who are interested. So in this video, we're going to have a go at coding our own neural network and seeing how well we can predict non-attendance. So let's get into it. So in this exercise, I'm going to be using a Jupyter notebook, link in the description if you want help getting set up with one of those. But what we're going to first do is start our new Python notebook. And we're going to call it predicting non-attendance. Okay, but what do we need to do before we can start solving any sort of machine learning problem? We need a data set. And where are we going to get that data set from? Well, thankfully, Kaggle has quite a helpful data set which we're going to use. And this, I believe, is called the medical appointment no-shows data set. So the first thing that we're going to do is download that data. Now, if you don't have a Kaggle account, you will need to create one. I've already got one, so I can just click download here. And we're using the Kaggle v2 May 2006 CSV. And what then we're going to do with that is take it and pop it into our folder. We're also going to unzip it. And this is a CSV file. For those who are not familiar, CSV stands for comma separated value. It's a bit like an Excel file, but it's recorded and every point is separated by comma. It's not that important, but essentially you'll be able to understand the data more once we've imported it. So let's get started. So firstly, we need to import our dependencies, and the ones that we are going to import, which are very commonly used in these sorts of problems, are pandas, numpy, and we will also import matplotlib. That should work. And then we're going to upload our data set. So we're going to call it no-shows, is the variable that we're going to assign. And we're going to use something called the read CSV function within pandas, which basically enables us to actually just call that directly into our notebook. But firstly, we're just going to check what the exact file name is. And here we can then copy that across. And hurrah, there we have got no-shows. And what we've done here is we've used the pandas data frame using PD to import this file, and now the data is in our environment. And this is quite nice because it just automatically structured it into quite a nice table, which can look quite aesthetically pleasing. So if we want to visualize that, we can use a number of different functions which are specific to this pandas library. So for example, we can use head, and that will show us the top 5 files within our the top 5 examples within our table. Other things we can also use is tail, which shows us the bottom 5. Sometimes that's useful if we just want to kind of have a look at how things might differ. Or if we just want to actually see the whole table, we can do no shows. But it is going to kind of stop it and not show us all of the data that's there. But if we just use, for simplicity, if we just use head, then we can have a look at our data. And let's have a look at the data table together. So what have we got? We've got patient ID, appointment ID, we've got their gender, the scheduled day, presumably the day that the appointment was scheduled, and the appointment day, presumably the day that it was then going to happen. We've got their age, we've got the neighborhood they're from. So this data set is from, I think it's from Brazil. I'm not too sure. Yeah, it It's not too clear. I'm sure we could find out if we look into it in more detail, but in the interest of time, we're not going to go too much into it. And then we have a number of variables here. We've got scholarships, hypertension, diabetes, alcoholism, handicap, presumably means handicap, and SMS received, so presumably if they sent a text beforehand or not. Obviously, if we had the time, and ideally we would look at all these different data kind of variables and see if there's a description of those and try and understand them in more detail. We're not going to do that today, but just from looking at that, we get a kind of idea of what this data set is about. There's a couple of things that would be quite nice for us to tidy up. So if we have a look here at some of the column names, for example, we've got hypertension. The English speaking of you may realize, I guess most of you probably are English speaking, but you may well realize that actually that's not spelt correctly. Probably more, I should say, the people from a medical background might realize that's not spelt correctly. And handicap, I think they mean handicap, so we probably need to correct that. So the first thing that we can do is just to rename the columns. And the way that we can do that is a function called .rename. And what this function takes in is details on the columns. So we will specify that the columns we want to rename are, and that's, if I remember correctly, I think this is taken in as a dictionary. Again, if you're not too familiar with all these concepts, if you've not heard of a dictionary before, then open up a new tab, Google it, come back. It's not too important for what we're doing, but there's various different data types, and I've covered it in previous videos as well. So we'll start with the columns, and we want to convert this into the appropriate name. So if we say hypertension should now be hypertension, then that should rename our column. And if we look there, it's now been renamed. Perfect. And actually within this, we can also go with handicap is now going to be handicap. And this might throw up an error now because hypertension, fine, it hasn't, because hypertension obviously already renamed it, but didn't throw up an error. And one thing that we'll also just use is something called in place sets true, and basically that's not important, but it just means that it doesn't return us the data. It doesn't show us the whole table. We can just make those changes and carry on. So now we're happy that that looks better. So if we again look at the head of the table, what else do we want to do here? One other thing we would like to do is, if we look at gender, it's currently stored as M or F, meaning male or female, and that is a string data type. But actually, if we're trying to train a model and we want to incorporate that, a string is not particularly helpful for the computer. We want it as a binary, so as a 0, 1 ideally, for male or female. And again, with no shows the same. We've got no, and presumably we've got yes elsewhere in the column. We would like to turn that into a 0, 1 as well. So let us just quickly make sure that we have got yes and no within the no show. And the way that we can do that is by calling our overall table, calling the no show variable, and calling a function called unique. It doesn't like that, and that's because you can't kind of enter the file in that way if we are, if it's not one word. So let's go with this, and we can see no and yes. So there's nothing else, and that's how they've spelt it, and we need to be able to use the same exact syntax when we then change that. And for male and female, we can do the same. So if we just put in here gender, then we've got F and M. So we know that there's not any other things included there. So now in terms of actually changing it, we want to again, what do we want to call for this? We want to do map. So we want to go with no shows gender equals no shows gender, but we're then going to map, and again we're going to use a dictionary of F going to 1 and M, just give us spaces there, going to 0. That should work. And now we can, if we can just recall this cell and check. Yep, so we've seen it's changed from 1 to 0, and let's just use the same thing for no-show. So if we copy that variable across, we don't want to change F and M, we want to change yes to 1, and we want to change no to 0. And again, if we call head, we now see that there's zeros. If we look at the unique values, it should now be 0 and 1 are the two unique values that we see, and we do. So that's all reassuring. So with that being said, let's tidy that up a little bit, and let's just re-examine the top of our table. And we've got some nice binary variables here, ones and zeros. We've got neighborhood, which we probably need to deal with. We've got age, which is numerical. We can use it in that form. We might want to scale it. We've got schedule day and appointment day. So those ones are going to be a little bit tricky for us to incorporate into the model because it doesn't like this very complicated date and time format. And the way that would be best for us dealing with this would be to actually convert this into the amount of time between when it was scheduled and when the appointment actually happened. So this is going to involve a few different steps, but it will involve learning how to use the datetime function and how to manipulate datetime structures. So let's get into it and have a look at how we can do that. So firstly, let us look at scheduled day. And we will we'll use the apply, apply numpy.datetime 64 function, and that should, in fact, before we do that, let me just confirm my suspicions, which is about the type of this variable. So it's a series, let's index in, so it's a string. So it is currently a string, which we don't like for incorporating into models. Computers like numbers, 0, 1, or numerical length of time. So we are going to need to change that into a date time. And let me just make sure that's right. I think it is. If we try with that, I should not actually have deleted that cell, because now I can check and we have got timestamp function, which then means that if we look at this, we should be able to do dt.date, and this should just return the date. And there we have, perfect. So we now have of this, and basically just to explain what's going on here. We initially had it as a string format, but the specific format of the string was in a structured way. So it gave the year, then the month, then the date, then the time in this same format, but it was still a string, which just meant that it's all kind of considered as text. What we did is we used the apply function to turn that into a date time data type. And it then looked at those orders, so it looked at the first 4 and thought, okay, well this is a year, so then 2016 is now a year, and it considers that to be a year. And then we've got 04, April, we consider that to be a month, etc., the date, and then the time. So now what we can do, which is quite nice, is we can look into this and we can say, okay, I just want the date. And if you just want the date, it's going to give you back the year, the month, and the day. And I believe if we went with time, yep, it would give us back just the time, so the second half of it. And that's very nice because that's something that we can work with quite well. And this is actually very useful for what we're trying to do, which is to look at the difference between the scheduled day and the appointment day, because now we have it as a date. And that just means we need to, and actually let's update the column to, and actually I don't know how well I explained what I'm doing here. So basically, one thing that's really nice about Pandas is when we update a column, we can actually just put no shows scheduled day, which what that does is it just indexes into that whole column. So here, to show you, if we go here, it's just going to show us that whole column. So that's this column here. We're using these square brackets, we're indexing into no shows, and we're seeing that entire column. What we can do is, with Pandas, we can update that whole column at the same time. So I can say, no shows scheduled day. This entire column is now being replaced with no shows scheduled date, but only the date. So it's taking that data, is looking, okay, this is the date, ignoring the time, that's getting thrown away, and then that is now the new column. So once we've applied this, and then we look again at no shows scheduled day, we can see it's only the date, and that's now what is in the column, and that's helpful for us. And let me show you why that's helpful, because the next step is to look at appointment day, and basically we actually want to do the same thing. So I'm just going to copy this down. Always copy code if you can. Is a good general principle to follow. So we're now going to change this, and it should be the same thing happening in this other column. So right now that column is a string, so it's text in this particular structure, year, month, date, etc. We're going to convert that into date and time, and then we're going to just pick out the date, and then that column is just going to become that date. So we now applied that, and let's have a look at the whole column, and here we have it. We've got the date and we've got the schedule dates. Perfect. And now the next part, which is perhaps the magical part, is that we can actually look at the difference between the two. Because it knows date, it knows that we can subtract dates, and it's automatically going to be very smart. It's going to look at, well, how many days are there between these two dates? So we can assign a new column, which we are going to call waiting time. And this column is going to be what you get when you take, which way around do we want to do it? Scheduled day, I need to think this through. Scheduled day minus appointment day. This needs to be a minus, not an equals. Now, is that going to give us a positive or negative length? I mean, one way is just to check it. What do I predict? I think it's going to be scheduled minus appointment. I think it should be the other way around. I think it should be scheduled here, and then minus appointment. And I think now, if we look at it, fine, so that's not going to show us the whole thing, but what we can do is our little function. What function? The unique function. And okay, fine, so it's giving us that in a date time format, but the only thing I care about is if it's positive or negative, and that in almost all cases is positive, which means what we have done is we've minused the date the appointment is going to happen, and when it from the day it was scheduled, and we're looking at that time difference. There is one case here where it's actually a negative, and that probably means that it was just recorded incorrectly, and one of the data points says that the appointment was actually scheduled after it actually happened, if that makes sense. Fine, so we're happy about that. Let's go back to our table. Oh no, sorry, I'm getting confused. We're gonna use head. So for the purpose of training our model, we're actually gonna ignore the column scheduled day, appointment day. We're just gonna look at the waiting time and see, maybe you would expect that if someone waited longer, they're more likely to not attend their appointments. What else do we wanna do? I mean, one thing we can do just to tidy things up is take away some columns that aren't relevant. So patient ID, appointment ID, probably doesn't look to be too relevant. It looks like it's just a number which refers to the patient or the appointment. So we can get rid of those, and there's a nice little handy function, which is drop. So we can, what is wrong with this? Yes, we need to specify the axis, and that's gone. And basically, as I understand, the axis is just whether it's going down or going across, and because it's a column, we want to say axis is 1, because it's going down. So now that's gone. And you want to be careful with this, because once it's gone, it's gone. And actually, if we now wanted to bring it back, we'd have to go up to the start here, and we'd have to rerun that and kind of go all the way through it. So we can call that, and then we can also drop appointment ID. It's not that relevant. We don't have to do that, but it's kind of just to show you how things work. Okay, one thing now, you might have noticed, look, patient ID is here. Well, we just dropped it. Why is that? Well, actually, what I've done is I've dropped it, but I haven't then saved the new table as the version with the dropped. So what we actually need to do is say now no-shows equals this version of no-shows where we dropped that column. And again, I need to do that at the bottom here. And it now won't return the table. So what we'll do that. Now that's our no-shows. We've got rid of patient ID, we've got rid of appointment ID, and now if we just call it, we should see that they have gone, and they have. Good. What else? I think one thing we can look at is do some kind of like sanity checks of the data. So we can have a look at, let's look at age and just see what sort of values do we have for age. Do we have any outliers? Do we have anything that's not really that realistic? The way we can do that, you might be able to figure it out ahead of me actually doing it. If you've been seeing some of the functions I've been using already, what we're going to do is we're going to pick the column, which is age, and we are going to call the unique, oops, a daisy, we use the unique function. We need the brackets in order for it to be a function and to be applied. And that gives us all the unique values. Instantly I can see there we've got someone who's -1, which makes me suspicious. If we want to make this a little bit nicer to look at, we can use the sort function. The numpy.sort function. So basically this means that within the NumPy library, there's a function called sorts. So if you do numpy.sorts, then it calls that function and it sorts it nicely in ascending order. I don't think there's anyone who's going to be -1, although, I mean, maybe that was someone who's pregnant. It's possible. And then, yeah, we've got a few pretty old people, 100, 102, 115. I mean, it's possible. I don't want to rule it out, but I don't know. We could look into that and maybe exclude that from a data set. We're not going to do that now, but these are some of the kind of things you'd want to look at. And you could also apply the same sort of principles to maybe any of the other columns. I mean, none of them here, to be honest, look too much like the kind of thing where you're going to have some kind of crazy values, but you would probably take your time and just look through all of these different columns to see what all the unique values are. Scholarship, hypertension, diabetes, make sure they're 0, 1s, that sort of thing. We're not going to do that now. We want to get onto training our model, and I know you want to get onto training a model. So anything else we want to do? One final thing which could be helpful is if we want to incorporate neighborhood into our model, what data type is it at the moment? It's a string data type. And strings, as I said, machine learning models don't really like them. So we want to convert it into something that can be used, and it really likes binary variables, 0, 1s. So there is a nice little function we can do with this, and the particular approach is called assigning it as a dummy variable. And basically what a dummy variable is, well, I will show you what it is probably the easiest way. So we will go with no shows dot, no, not no shows dot, we're going to use a pandas function called get dummies. And if I remember correctly, what this takes in is the columns. So we're going to say the dummy column is neighborhood. Make sure I spell that correctly with only 2 O's. And we are going to say that the columns equals the dummy col. And I think we want to also specify that we're using the no-shows dataset. I think I need to spell that correctly. And I may need to check the syntax here. Oh, that seems to have worked. Perfect. So okay. So what we want to do with that is actually assign the new table to what that is. Now, to explain what dummy variables are, basically dummy variable is when you take something like we saw of neighborhoods. So you have a number of different districts which are strings, but rather than keeping them as a string, we are going to make one new variable for every single possible neighborhood there could be. So let's say there's 10 different neighborhoods. Now each of those neighborhoods in themselves becomes a variable, and it becomes a binary 0, 1 variable. So we're either in that neighborhood or we're not. So for the majority of these, it will be 0 because they're not in that neighborhood. But then if you go all the way across, you'll see that there's one neighborhood where actually it is. And do we see any examples of that here? No, we don't. That's because the ones that we can see are Jardim de Peña, Mata de Praia, which are not here because actually there are quite a lot of different ones here. But if we do want to have a look at it, what we can do is say no shows.columns. That gives us a full list. I know it's because I haven't re-updated it yet. So now if I apply this, it's going to be re-updated. Now if we look at columns, it's going to have a long list of all of these different neighborhoods. And okay, so that was a lot. So I don't know if we would actually use these as dummy variables. Probably an alternative would be just not to include them in our model, but to demonstrate the principle, I've included them here. And what's one that we know? We know Jardim de Peña. So we would expect, Jardim, where are we? Yeah, so if we now index into this column, what we should see, so that is now looking at that entire column, the first value should be 1. And then we'll see we should see 1, 1, 0, 0, 1. Let's make sure, 1, 1, 0, 0, 1, perfect. And then it goes all the way down through all 110 different thousand data points. But those are all the ones in that neighborhood. Cool, so I think we're done. I think our data set is ready for training. So now let's move on to actually training our neural network. And the way that we're going to do that, so training the neural network, we are going to want to decide, what variables are we going to include first and foremost. What are the variables are we going to use for training? We can have a nice look at this column, and to be honest, I'm not going to use all those neighborhood values. There's a lot of them, but we do want to have a nice little look at our columns. We want to see what we have. These are the ones that we have, and we're going to include most of these in our model. So we're not going to use all of those. So let's call these training variables, or training vars for shorts. And we are going to, in our model, we're going to look at certain columns. And just take a step back. Basically what we're going to do is our predictive variable is no-shows, whether they attended or not. And then our training variables are all the columns that we want to then incorporate into our model. So our model is going to look at all those columns for each patient. They'll look at the column for each of those and then try and say, did they show or did they no-show, kind of thing. So we're going to look at gender. We're not going to use scheduled day and appointment day because we created waiting time for that. We're going to use age, scholarship, hypertension, diabetes, yes, alcoholism, yes, handicap, yes, SMS received, yes. Now we're not going to use no-show because that's what we're trying to predict. So it's not going to be shown that data. It's not going to know. The network is going to have to try and predict that. And then we've got waiting time. So those are all the variables that we want to include in our model. We're not going to use neighborhoods because there's just too many of them. And now that we've defined the training variables, we want to divide up our training data. So without going into too much technical detail, basically, we're going to divide it up into a training and a test set. And basically the reason we do that is we want to give the neural network some training examples. It will learn from those. And then we want to actually see how well it is doing in our test sets. Because what can happen is it can learn some patterns within that training set, which is actually only specific to that training set. It doesn't work when you try and apply it. So we need to hold up like a test set that it hasn't seen the answers for, test it, and then we see, well, actually it does seem to work on new data. So if we now apply it to the real world and it works on real data, then that's great. So in order to do that, we're going to import from sklearn.model selection, we're going to import train test split. And we are going to define trainx and test, no, just train and test equals, how exactly do you call this? So train test split, I think it's train test split on no shows. And we are going to, we will need to define the split. So the percentage that we're going to use, I believe we say test size 0.15, so that basically means 15% of it is going to be in the test set and 85% is going to be in the training set. I don't know if that's right, let's find out. Looks promising. So dot shape is really helpful as well. That basically just shows the dimensions. So we can see there's 93,900 training examples, which is more, is less. We saw there's a total, I think, around 120,000. So now that looks promising. And then shape should be in the region of like 20,000 or so. So 16,000, perfect. So it seems to have worked. Great. So the next step is to define what are the kind of training variables and the output are for the train and the test sets. Again, apologies if this is kind of tricky to follow. If need be, pause, have a quick think about it, try and work it out in your head, or rewatch the video, or find another video that explains it maybe better than I'm doing. But what we're going to do is we're going to take our training set and we are going to index only those training variables that we defined above. So the training vars. So basically what's happening here is at the moment we have our train variable, and what our train variable is it's these 95,000 or so examples, and it's all of our columns, all 27 columns, and it's 95,000 examples. What we're doing here is we're saying we only want the columns of the variables that we care about, the training variables. So that's now train X. We're going to do the same for, we're going to define train Y. We're going to define test X, and we're going to define test Y. So for test, pretty similar process. What do we need to change? We need to change train to test. So what this is doing is looking at our test sample, which is the other 16,000 training examples, so 16,000 rows. And again, right now it's all 27 columns. We are now saying that the X portion of test is just those columns. And we use X and Y to mean X, the variables going in, and Y is the output coming, that the model is kind of giving us out, if you're not familiar with that. So here we have train Y. Now what do we want for train Y? Well, we only want the column that we're trying to predict. And which column are we trying to predict? We're trying to predict no-shows. So we're going to index into that column, no-shows. And for test Y, we're going to do the same, but we're going to do it for the test set. Now that should work. It doesn't, probably because I've spelled no-shows wrong. Maybe it's capital S. And if we investigate, we can see it's a capital N, sorry. And it's also no-show from the looks of it, so no-show. So you need to be very specific with how you do it. So it is capital N, and then no show. Perfect. If we want to do a quick check on that, we can see that it is a nice long list of zeros and ones for no show or not, and that's what we're trying to predict. Perfect. So now that we've defined our training and our test sets, we need to define what model we're going to use. Now, you already know what model we're going to use. We're going to use a neural network. There's lots of different models that we can use that do classification tasks. So this is a classification task where we're trying to say, are they in this category, this classification of they did attend or they didn't attend? We're not going to go into detail about the different types that there are. I have made other videos on this, and I will make kind of other explanations, but we're going to look at neural networks, as I said. So we want to import our model. And again, we're going to use sklearn, nice and simple. And we want to, I think, import from neural networks. I might need to check this, but I think it's from neural networks. We want to import a nice simple neural network. Let's check, that's not right. What is it? Neural network. Not networks. Yeah, I mean, makes sense. Great. And MLP classifier, basically, it's just a kind of a shallow neural network. Fine. And then we want to define our model, which is going to be this MLP classifier, but just read neural network when I say that. And we're going to need to tell it some important information. So the information that we're going to tell it, don't want to go too technical, but these are like called hyperparameters. And that's basically things like the learning rate, which is how quickly your model updates things, different methods that it can use for updating itself and training itself, and lots of different things about the training process. I don't want to go into detail here because we're learning how to actually write the code and how to get it to work, and less about how everything works behind the scenes. But we are going to define I mean, probably a lot of these, there's already presets for, so we could get away even with just not calling anything. But we probably would like to define the layers, so the number of the number of nodes in our layers. So from looking here at the documentation, we can see exactly what sort of variables are there, and these are all the default variables for them. So we're going to go with some hidden layers. What's best? Yeah, it looks like we just use hidden layer sizes. I think, would that work? I think what we've done, and again, we can look into this, is I've now defined a neural network where we have the number of input variables that we define, the number of output variables that we define, which is basically 0 or 1. And then within that, we're gonna have, I think, 2 layers of 5. So we're gonna have input, which is going to be gender, age, 1, 2, 3, 4, 5, 6, 7, 8, 9 different input layers, input nodes, then going to 5, going to 5, and then going to 1 to predict. And the rest of it I'm going to leave as it is, and we'll just train our model and see how it does. And if we want to get technical, we can always come back and play around with those and try different variables and see what happens. For the purposes of this, we're just going to stick with that. So we now have basically defined our model, and in this model variable we have a neural network which has this structure, but it hasn't been trained yet, so it wouldn't be able to recognize anything meaningful. So what we now need to do is call model.fit, and that's going to fit our model to the data that we have. And in order to fit, it needs to have a training set where it knows the inputs and it also knows the outputs. And so for that, we're going to give train X and train Y. And now our neural network is training. It didn't like that because, I see. So time delta, and this is one of the reasons we need to standardize all the formats that we have before. So it doesn't like this column of waiting times because it is a time delta. And let's just check that it is waiting time it doesn't like. So if we pop up here and we go with no shows dot waiting time, I think it was it capital? It's going to tell us here time delta. So what we can do is, again, we can update equals no shows waiting time, and we can just actually apply, make it a, I think if we go with int, no, we want to go with numpy dot float 32. Okay, so I actually wasn't sure how to solve that problem, but I went away and I found a pretty nice answer on Stack Overflow, so I can just copy and paste that in now. This should solve our problems. And basically, from what I understand is here we're actually kind of working out the difference in time between the two variables at the time and then converting that into days afterwards. So what I did before is I converted them both into days separately, then I subtracted them, and then it didn't like that because it gave that still as a date time. It wouldn't let me convert it back. Here what I did is actually subtract them, then convert it into days, and then convert that number of days into an integer. So this should now work, let's see. But I guess main learning point here is, Stack Overflow is a really great website that has a lot of sources on these. So if you ever encounter a problem and you're not too sure, just kind of Google around. You'll find hopefully something good on Stack Overflow that explains the solution to the problem. And now I think we're good to go. So I'm gonna delete that columns variable actually. Fingers crossed, we're gonna redefine our training and our test sets, and model is training. This looks promising. So our neural network right now is updating all the weights between the different layers and learning how it can map those inputs, those outputs, if it's given a new test set. And we have success from the looks of it. Firstly, let's not count our chickens because we need to actually see it working, but it seems that it's fitted onto the training set. And the way that we can now test that is by asking the model to predict. So we used model.fit before, now we're going to use model.predict. And I'm going to use predict prob A. And basically, what this does, or I'll show you what it does, it will return two columns, which is the probability of it being in one class and then or in the other one. So this is quite helpful. It means this model predicts that for the first training example, which is the first row, there's a 96% probability that it's going to be not a no-show, so 0, and then a 0.35, so like a 3.8%, sorry, 3.8% probability that they are going to no-show, which is pretty nice to know. And what we can do, we can say that those are the predictions of prob A. And then we, for the purposes of quantifying the performance and kind of visualizing it, we will specifically index that first column, that second column actually, which is the no-show column. So let's have a look at that. And now if we look at prediction, it should just be a single column of the probability of predictions. So, I mean, it's showing it us here as a row, but essentially it's still kind of in a column format or whatever sort of, it's one-dimensional array. That's giving us the probability at each point of that being a no-show. And so some of these should be higher, some of these should be lower, but the question is how accurate is the prediction? And what we've given this variable is we've told it what the variables of the test set are. So we've given it the input, which is test X. We haven't given it test Y. So that's the real test of how well it's going to do. And what we can do is we can look at those performances side by side, and we can see, so it's predicted 0.3% probability, or it's 3% rather. What actually was it? Was it a no-show or not? Because if it was a no-show, it's not doing very well. If it wasn't a no-show, then it's actually doing quite well. And if the ones where it predicts higher are actually no-shows, then that's suggests that we're doing a good job of our model. So what we're going to do here is we're going to plot a nice graph to help us visualize this. And I guess as a rule, or maybe just kind of out of capacity, I never memorized the exact code for plotting these graphs. So I have a lot of helper kind of ready-made graph plots that I'm going to use. And I'm just going to go copy and paste one from elsewhere. So this is from something called sklearn. It's a metrics package, and it enables us to plot the ROC curve. So we want to put in our own variables into this. So test Y, which is the correct name, and then prob A predict, we have called it prediction. So let's pop prediction in here and test Y. And what this is going to do is it's going to look down the whole columns of our predictions and what really happened, and it's going to compare. And it should plot a nice graph, and it does plot a nice graph. Fantastic. Now, I'm not going to go into detail about what this graph shows. Simplistic answer is the red dotted line is random guesses. So you were right 50% of the time. Anything above that line to the top left, towards the top left, is a good. result. So the fact that our line is above that is fantastic. And the fact that, there's a decent space above that means actually it's not doing a fantastic job. Obviously there's space to go a bit further, but it's doing an okay job. And the score is 0.72. So the range there really is from 0.5 up to 1. 1 being perfect, 0.5 being random, so terrible. And 0.72, it's not great, but it's okay. And given that we didn't use that many variables, it does seem that they do have a reasonable ability to predict whether someone's going to attend or not. And there's a lot of different things we could look at within that. So we could look at other metrics for those interested, precision recall, and maybe even plot a precision recall curve. But we're not going to do that today for the purposes of our time and your attention. So yeah, I think that's a pretty decent result. We've predicted in a good number of cases. If you want to understand what this curve exactly shows, then I've left a link in the description below. Again, I've made other videos on this. And if you want to have a go at this at home, or maybe you've already coded along, then great. If you want to play around with different things, some other things that you could work on, you could look at playing around with these variables. You could maybe look at neighborhood. You could look at the geographical location and cluster them and try and see certain areas where things are better and worse. You could maybe play around with these variables a bit differently. I'm not too sure. Actually, this data set is relatively simple. There's not a huge amount of variation that we can do, but hopefully, that will be interesting, and this exercise has been interesting for you. And another thing you could also do is just playing around with different types of classifiers. So here we use the neural network. There are a lot of different types like random forest, support vector machines, logistic regression. These are all common classifier models, and actually it's pretty easy to play around with them. So we can just use sklearn. So if you go on the website here for sklearn, the full name is scikit-learn, and you can just pick classification code. You could look here and say, I want to use a support vector machine for classification, and just follow the instructions here on how to load it up. So same sort of process, you would import your model SVM, and what you would do is here you would say model equals SVM. You would fit the model in the same way, and then quantify the performance in the same way. So you can play around with different classification models, see which perform better, which perform worse. You'd also play around with the hyperparameters, which are all these things in here. So when we call our model, say MLP classifier, we've said the number of layers. We could change the activation, the alpha, which is the learning rate, the batch size, all these kind of things. Feel free to look at those if you're interested. We're not going to cover them today, but yeah, have a go, play around, see what you come up with. So that's everything for this exercise. We have learned how to import data from Kaggle, how to manipulate things in pandas data frames, how to tidy our data, how to get it into the right format we need to train the model, how to use out-of-the-box models from sklearn, how to kind of interpret those, plot nice little curves and just see what the performance is. And all in all, we developed a pretty decent neural network at trying to predict people who are not going to attend their appointments and potentially could save a lot of money. If you're interested, have a look at the paper that was published in Nature, which did all this kind of stuff, and actually obviously in a lot more nuance and a lot more detail, and achieved much better performance than 0.72. So I hope you found this video helpful and interesting, and I will leave links in the description to the other coding exercises that I've made, and I'll be making more, so be sure to subscribe to get updates on future coding exercises that I make. And also, if there's interest, there is an accompanying blog post and an accompanying copy of all the code that I'm going to write in here, so feel free to use those as you see fit. But that's everything for today. I hope you enjoyed the video, and I'll see you in the next one.